GCSE Physics, welcome to my video on specific heat capacity, everything you need to know. Don't forget, if you want more information on this topic, you can check out my resources on the My EdSpace website, or you could check out my live lessons, have a look at the link in the description of this video. So let's dive straight in. So the first thing we need to think about is the definition of specific heat capacity. The definition for specific heat capacity, which you're going to make sure that you need to know, is the energy required to raise the temperature of 1 kilogram of a substance by 1 degree C. Now, if you've watched my video on specific latent heat, you'll recognise that definition is quite similar to our definition for specific latent heat. The only big difference is that specific latent heat is about changing the state of a substance. We use specific heat capacity to work out how much energy we need to change the temperature. If you want more information on changing the state and changing the temperature, don't forget to check out my video on internal energy. Now, there is an equation for specific heat capacity which is here. It's delta E is equal to mc delta theta. Delta E is the change in energy, and we're going to measure that in joules like we always do, which we write as a capital J. This delta here, this guy, this means change in. So how much energy we're transferring to the system or how much energy we are transferring away from the system. Depending on if we're heating something up, I need to put energy in. If we're cooling something down, then energy will be coming out. So we can use this equation for heating up or cooling down. M is, as it always is, mass, which we're going to measure in kilograms, please. Make sure in questions about specific heat capacity, you're looking out for them giving you your mass in something like grams. They love to do that. To convert between grams to kilograms, remember we have to divide by 1,000. Mass is the only one that has a prefix, kilo, that we don't change. If we see like a kilometre or if we see like a kilojoule, we'll always change that. Kilograms is the only one that we never change. C stands for our specific heat capacity. So that is the specific heat capacity. I always think of C for capacity. We measure that in joules per kilogram degrees C, written just like that. And then finally, we've got delta theta, okay? The delta again means change in, theta is temperature. So delta theta is the change in temperature, and again that's going to be in degrees C because temperature is in degrees C. So let's have a look at how to use this equation. So we're going to calculate the energy needed to increase the temperature of 2.5 kilograms of water from 40 to 60 degrees. The specific heat capacity of water is 4,200 joules per kilogram degrees C. It's a good idea to remember that the specific heat capacity of water is about 4,000 because it gives you a useful reference point. Quite often questions in exams are going to ask you about specific heat capacity of water. They will always give it to you, but it's a good idea in case you ever get a question where you're expected to measure it to have a vague idea of the kind of number that you might be going for. So we're going to use our equation. So I'm looking for the change in energy. I've got the mass here. That's my mass. So 2.5 multiplied by the specific heat capacity, which is there, 4,200 multiplied by the change in temperature. Now we've gone from 40 to 60 degrees. So the change in temperature would be 60, take away 40, so it would be 20 degrees C. So we're going to do 2.5, the mass, multiplied by 4,200, the specific heat capacity, multiplied by 20, the temperature, which gives us an answer of 210,000 joules. And that's how much energy we would need to transfer to this water for it to raise the temperature by 20 degrees. Now, there's also a required practical that goes to specific heat capacity, which I'm going to talk you through now. Okay, so this is our specific heat capacity required practical. I'm sure that lots of you have seen this before, where we are heating a metal block with an immersion heater. Now, you might have used either one of these two setups. This one here with a joule meter, or this one here with an ammeter and a voltmeter. I'm going to talk you through both. So, this diagram here, this is our metal block. Metal block, the same as on that one as well, okay? This here is my heater. We call it an immersion heater. So that's what I'm using to heat the block. And here I've got a thermometer, okay? Now, this object here is called a joule meter, and it measures the amount of energy going into this heater here, okay? Joule meter measures joules, measures energy. That's quite obvious. So this here is a joule meter. So for this practical, to measure the energy, we use a joule meter. To measure the mass of the block, we would use a balance. To measure the temperature of the block, we would measure the initial temperature and the final temperature. And then because we're looking for the change in temperature, remember that would probably be a marking point in a 6-mark question, is how would you find the change in temperature? We're going to do the final temperature minus the initial to give me the change in temperature, okay? Now, if you don't have a joule meter available to you, you may well have used this method to measure the power of the heater, okay? I've got an ammeter and a voltmeter connected to my immersion heater with a power source. So again, this is my thermometer. This here is my immersion heater. Now, I need to find the power of the immersion heater first. To find the power, I'm going to do P is equal to I, the current, multiplied by V, the potential difference. I can measure this using an ammeter, and I can measure this using the voltmeter. Okay? That's going to give me the power of my heater. Once I know the power of the heater, that's the amount of energy that's transferred every second. I then just need to time how long that heater is turned on for. And I can use the equation energy is equal to power multiplied by the time. So in this setup, to measure the energy, I need to time how long the heater is on for, and then I can find the energy by multiplying the current, the potential difference, and then multiplying both of those by the time. Now, once I've got my result, I can either just take the total amount of energy transferred by the heater, divide it by the mass of the block and the change in temperature to find the specific heat capacity, or what I could do is I could take the measurement of the energy and the temperature every 30 seconds for 10 minutes and plot my results on a graph. It should be a straight line graph that looks something like that. Okay? Now, please take care to make sure that you give your graph an appropriate axis if you're doing this. Okay? For example, if I'm heating a metal block from 20 to 40 degrees, I don't want to start this x-axis down at 0, okay? I'm going to start it at 20. I'm going to do what's calling truncating my axes so that my data takes up over half the available space. Once I've got my line of best fit, the gradient, which remember is the change in y divided by the change in x, so that would be the change in y, that would be the change in x. So the gradient, which is change in y divided by change in x, would be equal to the mass of the block multiplied by the specific heat capacity. So to find the specific heat capacity of the block, I would take my gradient and divide it by the mass of the block that I found originally using my balance over here. Common problems with this experiment involve the fact that energy is transferred from either the heater or the block to the surroundings, or that we waste energy heating up the heater before the heater starts to heat up the block. Ways to improve this experiment involve insulating your block. You can use a heat-proof mat to insulate it from the table that it's on to stop heat from escaping that way. Or you could put thick foam around it or padding around it to insulate it from dissipating its heat to the surroundings slightly. You could also choose to preheat the heater so the energy is going into heating the block rather than heating the heater. All of these things will improve your value for specific heat capacity. I hope you found this video useful. Don't forget to check out my resources on the My EdSpace website. You can have a look at the link in the description of this video to have a look at joining my live lessons. And don't forget, while you're there, to hit subscribe. Thank you so much, and I'll see you in the next session. Bye.